Hey guys, welcome to our lesson for section 6.4 on other trigonometric functions and their graphs. So again, what we're going to start basing this all off of is based off of some angle in standard position where x, y is some coordinate point on the terminal side of that angle, and r is the radius of that angle. And we can find r very simply using this distance formula that is derived from the Pythagorean theorem to get this nice definition that we have here. And so this is something that was talked about in 6.3. So if you haven't watched that yet, make sure you go back and watch that. So we let xy be a point other than the origin, so it's not 0, 0, on the terminal side of an angle theta in standard position. If r equals the square root of x squared plus y squared, then the six trigonometric functions are as follows. For angle theta, so we have that sine of theta is y over r. Cosine of theta is x over r. Not Jan. Tangent of theta is y over x, where x does not equal 0. If x does equal 0, we get undefined. And as we saw in 6.3, at places where x is 0, we get these tangent lines. And so the graph of the tangent function got all crazy and screwy. And we're going to see that again today with some other functions. And so then the other three function, we have the lovely cosecant of theta is just the reverse. So it's r over y. So y cannot be 0. We have our secant of theta. So we get r over x. So x cannot equal 0. And lastly, we get our cotangent of theta, which is x over y. So y cannot be 0. Now you may ask, how come in sine and cosine there's no blank, r can't be 0? And the reason for that is because, very simply, this point is something other than the origin, and r is, the way it's calculated, is it's simply the distance from the origin to this point. Now distances cannot be 0 unless it is the distance between the same thing, and since xy is not the origin, r cannot be 0. So we get these lovely six trig functions. Now, there are some identities here that I'm just kind of throwing at you and saying, hey, bam, you get this. The derivation of these, if you want to look at the textbook, they give a little more kind of information, but it's not really something that is too pertinent to the use that we're going to have for it in this class. But we get that tangent of theta is equal to sine of theta over cosine of theta, and cotangent of theta is cosine of theta over sine of theta. And where that really comes from is very simply, if you look at tangent being kind of the opposite over adjacent, and if you look at a kind of, we'll have our standard angle, that's a terrible. So if we have our kind of angle in standard position here, and we create this little triangle, right? We think opposite over adjacent. Opposite over adjacent. That opposite is our y value, which is involved in our sine, and the adjacent is the x value involved in our cosine. And so we kind of get this nice little relationship where tangent is y over x of sine over cosine. And just because it's fun, I'm going to do it a little more. I'm going to go a little more. So let's see here. So why is it not? Sine of theta over cosine of theta. Well, sine of theta is y over r. Cosine of theta is x over r. And when you divide by a fraction, that's the same as multiplying by its reciprocal. So we get y over r times r over x. These cancel, and we get y over x, which is tangent of theta. There, I showed that one. Do the exact same thing for cotangent. So start with cosine over sine, x over r over y over r, multiplied by the reciprocal, r's cancel, you get x over y, which is cotangent. Now, so the Pythagorean identity, this is a very important identity here. I don't want to like kind of, whoa. I don't want to underplay how important this is. It is something we are going to use extensively, especially in chapter 7. So make sure that you guys are comfortable with this, as it is something we are going to use a lot. And so with that, I'm not going to really derive that one again. You can look in the ebook and you can see that there for yourselves, but I don't want to waste more time with that. That's just a very important one. So sine squared plus cosine squared equals 1. And that just comes kind of very similar idea, Pythagorean theorem with the triangle. So what's really cool is with this information, this kind of X and Y information, and thinking about these quadrants, we can actually do things like this. We can be given a sine value of some angle theta, and then knowing simply that cosine is either greater than 0 or less than 0, we can find all the remaining 5 trig functions. And so what we have to do is, so we know that sine of theta is 4/5. Now I'm going to give us a little triangle over here. So let's say this guy is our theta. So what we know is sine is opposite over hypotenuse. So that means this side here is 4 and this is 5. Well, now I can use the Pythagorean theorem and we can calculate our adjacent side, which for those of you who are not familiar with special right triangles or special Pythagorean triples, Pythagorean triples are 3 integer values that satisfy the Pythagorean equations. And this is one of those. And so I know that this is a 3 because 3 squared plus 4 squared equals 25. Square root of 25 is 5. So there's Pythagorean triples are really cool. If you know them, there's 3, 4, 5 is kind of the smallest one, and any multiple of that. So 6, 8, 10 is a Pythagorean triple as well. 5, 12, 13 is a Pythagorean triple, and so you can find some more out there. But if you ever see 5 as a hypotenuse and then either 4 or 3 as one of the sides, you know the other side is the other 4 or 3. If you see that, say the two sides are 5 and 12, you know the hypotenuse is 13. So if you want to, those are some that you can maybe sock away in the back of your head, but really quick and easy to solve that if you needed to. So this tells me that I have a 3, 4, 5. But is that 3 positive or negative? Because I don't know which angle or which quadrant this is in, but because I am told that the cosine of theta is less than 0, that means that for that to be true, this 3 must be negative. And so what we end up with is this is our angle in standard position. And so we'd say that this is the angle theta we are talking about. Okay. So this is our angle theta, where this point right here is the point -3, 4, which gives us a radius of 5. And so now we know our sine function. We're given that. We can easily find our cosine of theta. And that's just going to be 3/5. Tangent of theta is just going to be 4/3, right? Because tangent is y/x. And then we can get our secant of theta. Our cosecant of theta, our secant of theta, and our cotangent of theta. Now we know that all of these are simply the reciprocals of their kind of pair in the sine, cosine, tangent. So cosecant pairs with sine, so the reciprocal of 4/5 is 5/4. Secant pairs with cosine, the reciprocal of 3/5 is 5/3. Cotangent pairs with tangent, and the reciprocal of 4/3 is 3/4. And so that's it. There is our lovely little values. So this is a really kind of very common problem. I guarantee you're going to see it on a test. If that is any, indication that you guys might want to know how to do these problems. So let's look at our second example. So we want to find the values of the remaining 4 trigonometric functions, given that cosecant is negative 17 over 15 and secant is negative 17 over 8. Now this is really cool because we're given all three values that we need to find all of our things, and we're given their signs, which is really nice. So if we remember that r is the radius, right? So it's the length from the origin to the point. It is always positive. R is always positive. Okay. R is greater than 0. Always. Okay. So what I know is this triangle, this angle in standard position, okay? So it is going to be roughly here-ish. So we have the point negative 8, negative 15. This is our angle. And I know then this R value here is 17. 17. Okay, so we need to find our sine of theta, cosine of theta, tangent of theta, and our cotangent of theta. So because we know our x value and our y value and our r value, we can do all of these. So our sine is very simply negative 15 over 17. Now, another way to do that, other than saying, okay, the y value is negative 15, r value is 17, we also know that the sine pairs with cosecant. It's the reciprocal. So the reciprocal of negative 17 fifteenths is negative 15 seventeenths. Cosine, we get negative 8 over 17. For tangent, okay, because that is our lovely y over x, okay, our sine over cosine, we get positive 15 over 8. And then cotangent is just the reciprocal of that. It's 8 over 15. That's it. It's easy. Okay. Now, quick refresher. That is the graph of sine. This is the graph of cosine. And then this is the graph of tangent. So those were the graphs we talked about last section. So we're going to now look at the graphs of cosecant, secant, and cotangent. Now, I'm going to tell you that we are not going to use these very often as far as sort of problem solving or problems that we're going to use. They are things that you need to know, and so we're going to show them. I'm not going to go through and do the whole table method. I'm just going to kind of give you guys some things. So negative pi over t, I don't like where that graph was. There we go. Negative pi over 2. Negative pi. Negative 3 pi over 2. Use that a little more. And negative 2 pi. Pi over 2. Pi. 3 pi over 2. 2 pi. So cosecant, remember, is, let me scroll all the way back up here. Okay, cosecant is r over y. Okay, so anytime y is 0, it's undefined, and we get a tangent line. Okay, so r is 0. or our y is 0, sorry, our y is 0 at 2 pi, negative 2 pi, pi, I don't want, let's do red, and we're going to dash at 0, and 2 pi. Now, the thing with sine and cosine, if we think about triangles, the hypotenuse is always the longest side. And so when we have sine and cosine as opposite over a hypotenuse or adjacent over hypotenuse, we are always going to have a number that is smaller on top divided by a number that is bigger, which means the max those could be is either 1 or negative 1. Now, if we reverse that, if we take the reciprocal of those, so we're looking at cosecant, secant, the smallest those could be is 1. Okay. Now you may ask, how do we get 1, right? That would be on the axes and stuff like that. So what we end up with here, okay, is we end up with these kind of loopy, whoop. Okay. We end up with these loopy things that do this. So they come up, and this is a terrible drawing because I'm terrible. Let me just make this. That's my negative 1 now. They come down to 1 and go back up. They go up to negative 1 and go back down, and we get this sort of thing. Cosecant is extremely similar. That's cosecant. Secant is extremely similar, and just like sine and cosine, how they look very similar. If we actually continued this graph of cosine, it's just going to do the same thing again. So if instead of picking up this kind of 0 to 2 pi range, if I picked up this range here, it would look very similar, right? Or if I pick up, say, this range here, right? And so depending on what we look at, what section, sine and cosine look very similar, just kind of shifted kind of left or right, if you will. It's very similar for cosecant and secant, which makes sense because they're based on sine and cosine. And so again, we're going to have a very similar setup here. Negative 2 pi, 3 pi over 2 pi, negative pi over 2, pi over 2, pi, 3 pi over 2, 2 pi. Now, with cosecant, our value was r over y. For secant, our value is r over x. So anytime the x value is 0, we get these undefined areas. And so here, our undefined areas are at negative 3 pi over 2, negative pi over 2, pi over 2, 3 pi over 2. Okay. Again, it's only going to go down to up to negative 1 and down to 1. The difference is that we kind of start a little differently, but notice that little start was different, but then from there, it's very similar again. We just have this kind of alternating thing. It's just like that. I don't want to get too much into these. Again, these are something that we need to know what they look like. We need to be able to understand how they work. One of the most useful things with these is understanding the range, and that's something we're going to get into more in 6.5 when we're talking about graphing these and so forth. And so now I want to go back and look at tangent. So notice tangent starts down and to the left, and it kind of comes up and to the right, right? So it's down to the left, comes up to the right. Okay. Cotangent is the opposite. Okay. Since tangent is y over x, cotangent is x over y. So again, anytime the y is 0, we get these asymptotes. And so that's why our asymptotes are at the same spot as they were with secant or cosecant. So tangent started down and went up like that. Okay. Cotangent does just the opposite. It starts up, works its way down. Okay. That's it. I mean, it's really that simple. And so I don't want to beat a dead horse with these. I don't want to get too over the top. You have calculators that can graph these. If you have an older 83, anytime your 83 gets a tangent line, so let's say we have a graph and you've got a tangent line right here. And so your graph does this and then like this. Your calculator, what it'll do is it'll kind of go like this and it kind of will come straight down. So if you have an older 83 or something like that, and you see these and go like, wait, there's supposed to be a tangent line here. That's what's happening. Your calculator isn't able to graph kind of disjointed graphs. So like how this piece here isn't connected to this piece here, or up here. And so your calculator isn't able to handle that in the way. So what it does, it just connects them with a vertical line, basically. So make sure you guys are kind of being cautious with these. Again, all of these were graphed in radian mode. Notice all of my x values are in radians or pi over 2 and stuff like that, not degrees. So make sure you guys are taking care when you are looking at these graphs and that you are looking at them in the correct mode. That's it for this section. Pretty short, sweet. So you guys have a great day, and I'll see you guys for section 6.5.